Hi everybody, welcome to this new IZDWF repair video. I have on the bench another of Mr. Lee's Commodore PET computer. This originally was a PET model 4016, but as we are going to see, someone tried to upgrade it to 32 kilobytes. Of course, I've only got its motherboard shipped to me. Notice that even in this small portion of the PCB, we can spot many socketed chips. Making a first visual inspection of the board shows indeed quite a few socketed integrated circuits here and there. Mr. Lee explained that this was done in part by the previous owner and in part by himself to try to bring this computer back to life. I usually don't accept repairing such heavily reworked PCBs, since many new problems can be created with such a massive IC removal work. However, Mr. Lee accepted the possibility that I would not be able to fix this machine and give up the repair at some point. The first thing to do in situations like this one is to carefully inspect the solder side of the PCB, trying to spot and correct any obvious damage. The repair started to look more difficult as soon as I spotted some missing pads like the one circled in red. During the previous repair, one missing connection was also restored with a wire. Since the situation looked worse than I expected, I decided to just remove the flux residues and then use a more effective approach to identify the broken connections that were likely a subproduct of the PCB rework. Since one major reworked area is under the RAM chips, probably to install all sockets needed for the 16 kilobytes that have been added, I decided to test every connection going into all RAM chips. This is not terribly difficult, since most of the signals go to all 16 RAM ICs, like all the supply pins, all the address pins, and the RAS and write signals. Cast 0 goes only to the odd-numbered ICs, and Cast 1 goes only to the even-numbered ones. Each data line goes to two ICs on pin 2 and 14, so all I need to do is check one connection for each signal, then check continuity on the same pin of all RAM chips, or just the one that are supposed to be connected. At this point, I decided to power the board and check for the presence of all the 3 DC supply voltages, and all looks good. The next step is checking the reset circuitry. Starts low, then goes high, so it's good. Then CPU clock, which is okay too. Now I want to exclude as many faults as possible, and since all the most important chips are socketed, and since I still have the other universal PET PCBs, I decided to first test these chips. The first suspect was the address decoder that has 2 soldered pins. One of the pins fell off as soon as I extracted it from the socket. However, I could reattach it just to test the IC on another board, and the chip was not working anyway, so I have replaced it with one of the spare chips that were provided by Mr. Lee. Then I tried both the 6520s, and they also were faulty. The 6522 did not work too on the other PET, so all of them were replaced with good working spares. The CRT controller was also getting very hot, and this was also replaced with a spare chip. When I received the PET boards, the CPUs were actually misplaced. The one in this board has a date code of 1984, while a lot of chips have a 1981 date code. So I found the CPU with the correct date code on another board, and sadly even this 6502 did not work correctly when put on an otherwise working motherboard. A failed 6502 is a rare find in my experience, so I tend to believe that this motherboard must have suffered some catastrophic fault at one time that probably killed all the big chips. Luckily, among Mr. Lee's spares, there was also this 6502, which is clearly a remarked chip because of the impossible date code. However, I could tell with some simple multimeter checks that this chip is indeed an NMOS 6502, but probably not a MOS technology one. I showed on another video how to test and decide if a remarked 6502 is NMOS or CMOS. You'll find a link to that video in the description down below. Since all the ROMs have been already socketed, it's again a good idea to test them all. I have most of the PET ROM images archived on my Data IO 2900 device program. It is a bad one. Notice how it reads a bad byte only on the even addresses. That's failure. And another bad one. This one instead has issues on all addresses. This one gives an insertion error. Basically, it means that the program is seeing too low or too high current on some pins. However, we can force the program to read the device anyway by disabling the continuity checks. But yeah, this one is bad too, as it always reads the same byte on all addresses. I've only showed the failing ROMs. The other 3 ones were fortunately good. These ROMs, however, don't look like they were unsoldered from a PCB, so it would be interesting to know all the past repair history of this board. At this point, I've decided to install my RAM-ROM PET daughterboard and finally connect the video output and have a first look at the current status of this PET. If you're curious about my PET daughterboard, you'll find a video link in the description. That's interesting. A solid pattern like this usually happens when the character generator ROM is bad or missing entirely. However, I just tested all ROMs and the chart gen was a good one. Let me try to move that ROM slightly. Yeah, it must be another marginal contact on this socket. Likely, the ROM is missing one of the connections on some of its 3 chip select pins, so let's see what we find. Pin 21 is chip select 3. And the same signal goes also to pins 1 and 13 of UB12. But here CS3 looks unconnected. The missing connection is right at the pin. So I add a wire from this wire. And now we can try again. So far so good. I hope we are getting closer to fix this one now. Now I have replaced the bad ROMs with some of my spare ones and jumpered the daughterboard to use the motherboard ROMs. The machine boots fine, so this means that there are no data bus conflicts. However, when jumpering the daughterboard to use the mainboard RAM, this PET looks still completely dead, so I decided to inspect the PCB again, and sure enough, this jumper, added to upgrade this board from 16 KB to 32 KB, was not soldered, although it was inserted in the right hole. After soldering the jumper, however, there was still no life, so I decided to jumper the daughterboard to run a test ROM. Usually, when this test code suggests a single bad RAM IC and we already excluded a data bus conflict, then it's likely a correct indication. So I removed UA15, checking that I didn't do any damage to the pads and traces on both sides of the PCB. Then I soldered a socket and installed a good 4116 dynamic RAM IC. The diagnostic message is now A7 address bad. This, in my experience, is of no much help other than indicating a generic issue with the lower RAM bank. The first thing I want to do is to look with the oscilloscope at the address and control signals of the lower RAM bank and see if anything looks suspicious. Since the upper bank chips are all socketed, I remove them all. They will be reinstalled only once the issue with the first bank has been resolved. And the first obvious issue is with the RUS signal on pin 4. That's clearly a bad level that shouldn't happen. I suspect that one of the AC has a shorted RUS input, so I want to see with the current tracer if I can identify the right one. No current on this one. Also not here. Nothing here. This is okay. On this one too. Some current on UA9. And definitely lots of current on UA7 pin 4. Seems also on UA5, but that's a good one. Yes, I think I'll remove UA7. So I pulled UA7, I soldered a new socket and installed a non-good IC in it. But it was not it. We have the same error. And still the same bad level on RAS signal. So let me check again with UA7 not installed. After UA9, there is no high current on the RAS trace. The probe shows current on the RAS trace that goes to UA9, so it must be it. This time I decided to just cut away UA9 from the PCB to minimize the possible damages to pads and traces. Unfortunately, that was not it again. Still the same error and still bad levels on the RAS line. I tested the UA7 that I pulled first and it was good. UA9 was also likely good, but unfortunately I cut all its pin as you have seen before. This scope image was already telling me all that was going on, but I haven't reasoned enough over it. We can see that the RAS signal shows both a correct high level and some too low levels. Now, when we have a shorted input, what usually happens is that we only see a too low voltage when the signal tries to go high, but we don't see any interval with the correct voltage for the high level. A situation like this instead happens when there are two outputs shorted together, and when they happen to be driving different levels, the resulting voltage goes close to 1 volt, since in the TTL world that 0 is stronger than the 1. The current tracer was indeed showing high current due to the short, but it was picking the current from the PCB trace only and not from the IC pins. A short can be likely between adjacent pins, but also between opposite row pins. And here it is, pin 4 to pin 13. A stupid short all this time. Now I want to find under what socket this short circuit hides. This multimeter is sensitive enough to give me a correct indication in cases like this, but I first checked all sockets just in case. I could determine with good confidence that the short is under UA5 between pin 4 and the trace that goes between pins 4 and 3, which is the one connecting to pin 13. So, what options we have to try clearing a short like this one? The PCB under UA5 is already damaged, so removing it with the soldering iron is out of question. If it was a different kind of socket, I would need to cut it in pieces and remove one pin at a time. Luckily, this kind of socket with round holes leaves some space between the plastic assembly and the PCB, so I can try to put a lot of liquid flux under the socket and use the smallest iron tip I have to try to remove enough solder and clear the short. After a few attempts, luckily, the short was gone, with only minor damage to the plastic of the socket. Now the rust signal looks fine. However, we still have the same message. During the editing of this video, I realized it was getting too long if I had to show all the issues and fixes at once. So the first part video ends here. This PET repair started on September 16th, and the last video footage shown on this first part was recorded on October 1st. And the last video footage of the complete repair was recorded on October 13th. Of course, I do these repairs only during the spare time, but still, most of the Commodore PET repairs that you have seen on my channel did not require more than 3 or 4 days on average. At about this stage, during the repair, I informed the owner of this machine that I was seriously considering to give up on the repair. However, I always hoped that every issue I was fixing was the final one. A lot of the remaining issues will be shown in the next video. I hope this one was interesting and that you learned something. I hope you'll be returning to my channel. That's all for now. Have a nice time and thank you for watching.